Welcome to the, hello everybody. Welcome to the Satellite Applications Virtual Training for Students organized by the MS Satellite Meteorology, Oceanography and Climatology, SatMOC Committee. My name is Jun Wang. I'm a professor in the College of Engineering here at the University of Iowa. I'm one of the SatMOC members. Besides me, there are also a couple of others members that has helped to organize this summer training session. And we have actually done quite a bit of the work, and their name will be recognized on the website, in the MS website, and I will show the links for the website in the chat. Today is actually our fourth and the last training session for the summer in 2021. And in case you have missed, all the past meetings sessions have been recorded, and they can be accessed via the MS website. For this training session, we are delighted to have Cara Wilson, together with her colleague Chris Jackson, both from NOAA, to talk about monitoring changes in sea ice at a seasonal and near real-time scales. Cara is a satellite oceanographer for Environmental Research Division at the NOAA's Southwest Fisheries Science Center in Monterey, California. And he is also a PI of 2 regional nodes of NOAA's Coastal Watch program. And Sarah, with that introduction, you have the floor.
Great, thank you, John. So I am going to be talking today about monitoring changes in sea ice at near real-time and interannual timescales. Chris Jackson is one of my co-authors. He is also from NOAA, NOAA STAR, which is part of NESDIS. And then my other co-authors are Jennifer Savajan and Dale Robinson, who are part of the Polar Watch team that we have, which is part of NOAA's Coast Watch. So to get started, I just want to do a little bit of logistics. We are going to use Slido for poll questions and answers. If you've been going to these sessions before, you should be familiar with Slido, but basically you just open a separate browser tab and you'll want to keep it open for the duration of the session. Just go to slido.com and then enter the meeting, which is SatMOC training-4, as you can see here on the screen. We're asking if you enter questions not in the Zoom chat, but rather in Slido, because that way we'll have a record of it. This session is being recorded, as John said, so if that's so be aware of that, and the video will be available on the AMS website afterwards. So if you missed it, or you want to see it again, or you want to recommend other people to see it, you can do that. So let's go to Slido now. And these are the questions that are shown here on the screen are the ones we'll ask in Slido. So I will go to Slido. So the first question is, did you watch the introduction to satellite sea ice data video? I watched it. And it looks like most people did. Great. Oh, okay. One person didn't. That's okay. A lot of the there's 1 or 2 slides that I'm going to show today that were also in that video, but there was also a lot of information in there that I'm not going to go over. And particularly, there's a lot of information in the intro video about different data products that we have on Polar Watch. So you might want to look at that if you're interested in getting more information about the data products we have in Polar Watch. The next question, did you watch NASA's disappearing ice video? Oh, I guess I should answer. Yes, I watched it. Most people did. Yeah, it was a kind of neat. It's a kind of short little video. NASA has a scientific visualization studio that does a really nice job at putting videos and animations together. And it had what I really liked about that video was seeing how the ice moves. And Chris is gonna show some more images about that as well. But it really kind of nicely showed ice moving around in the Arctic, which I thought was kind of neat. The next poll question was, did you read chapter 8 of the online R and ERDAP tutorial? I'm going to be showing a demo here later today using R. And so I was just curious to see if you'd sort of done your homework about using R and ERDAP. Ah, and most of you did. Great. Okay. If you didn't, don't worry. Feel free to ask questions as we go along. Are there any questions in the, no, there's no questions yet. Okay. All right. I think that's all the Slido questions I wanted to do for now. So let's go back to the presentation. Oh, no, there was actually another question. What do you want to get out of this session? Okay, let's go back to Slido. So what do you all want to get out of today's session?
And this is an open text question, so people can kind of give their own answers.
Yeah. Don't all type at once. Well, I guess programming plot of icebergs. Okay. Better understanding about polar sea ice in regards to climate change. Nice. Learn how R and ERDAP can work together. Access and visualize sea ice data. Great. All right. Well, I think we will definitely. Now, I wasn't going to talk too much about icebergs, but the other points we should all get to. So let's get back into it. I will go back to PowerPoint and. So a quick agenda. What I was going to start off with is talk about some of the sea ice data providers. There's a number of sea ice providers. This isn't an extensive list, but there's the National Ice Center in the US, there's the National Snow and Ice Data Center, and then there's PoloWatch. So I'm going to talk briefly about each of those data providers. And then Chris Jackson is going to talk to us about synthetic aperture radar data. And that's sort of looking at data on, or looking at sea ice on a kind of near real time or shorter time scales. And then the latter part, we're going to talk about looking at longer time scales of sea ice data. And we're going to access sea ice data from PoloWatch with ERDAP and also with the browser that PoloWatch has. And then we're going to end with using R to access some sea ice data from PoloWatch and make a graph of it. So next Slido question, do you use our software? And let me go back to Slido for that. I do. Okay, most of you don't. That's interesting. Okay, I think a lot of you use Python because I know session 2 used Python. It's a programming language. It's a lot of people in NOAA use it. It's free. Anyways, I will be doing a demonstration using it. There's a notebook which I actually uploaded onto the course website. So that is there. So if you do use R, you can download that. If you're interested in learning how to use R, you can. It's always the easiest way to learn a language is to take somebody else's code and start from there. But when I get to that, I'll make a point to sort of try to explain in more detail what I'm doing in R, since most of you are not familiar with R. Not a problem though. All right, let's go back to the PowerPoint. Okay. Oh, okay. Sorry, I forgot that I wanted to do more Slido questions. Not quite so organized today. So these are easy questions. If you have watched if you watched the video, which of the following sea ice products can be estimated from satellites? And I'm actually going to give the wrong answer to see so I don't give it away. So what did you all say? Yes, all of the above. As I said, that was an easy one. Really just to drive home the point here that there's a lot of different products that one can get. So when we're talking about sea ice, there's sea ice concentration, there's thickness, there's the type, which is very much correlated with the age. There's the ice edge, and it really, depending on what you're doing, what your research application is. If you're navigating, you really maybe just care about the edge. But thickness can come into play because there's, depending on what kind of ship you're on, they have limits of what kind of thickness of ice they can break. So there's a lot of different things that people want to know about sea ice. So it's kind of, it's a little complicated. All right, next slide of question. And then we'll get back into the presentation. In what frequency are sea ice measurements made? And I will say the infrared and see what you guys say. Yes, all of the above. That's the other nice thing about sea ice, but why it's also can be complicated is there's a lot of different ways to make the measurements. You can make them in infrared, you can make them in the visible, you can make them in the microwave. So there's a lot of different sources of data as well to look at. All right, now let's go back to the PowerPoint. So we've gone over that. So let's start off by talking about Polar Watch. If you were at the session last time, I was talking about Coast Watch, which is a NOAA program. It's out of NESDIS, which is the National Environmental Satellite Data and Information Service. And Coast Watch, the aim of Coast Watch is to help access to oceanographic satellite data products. And Polar Watch is a relatively new node that was set up recognizing that the polar regions where you want sea ice were sort of left out of the nodes that Coast Watch had, which were pretty much just around the coastal areas of the United States. So Polar Watch was set up to facilitate satellite use in the polar region. So not just sea ice, but also the other satellite products that we have. And so it serves as a place to bring together all of those satellite data sets in the polar and subpolar regions. And there's a number of issues that come up in when you're working in the polar regions. The most obvious one is issues of projection, and the maps that we're looking at here don't really work in the polar areas when you want to look at polar projections. And so there's issues with how the data is projected and how it's gridded that can come into play when we're looking with polar data. So some of the data sets that we have, when I say we, Polar Watch works with NSIDC, the National Snow and Ice Data Center, and the NIC, the National Ice Center, which are both, which also provide data. And so Polar Watch is we sort of curate data. So we sort of pick and choose data sets that we think will be of use to our users, and we incorporate them into our data distribution service so that they can be more easily accessible. And then we serve our data, level 3 data, on an ERDAP server. And if you were on the session last week, I talked about ERDAP a lot, and I'm going to be showing you how to access data from ERDAP at the end of the session. So just a little bit more about Polar Watch. Actually, I think I pretty much said all of this, but it's not just sea ice, but water temperature, ocean color, salinity, winds. These are all satellite products that we can have in the polar regions as well. And we just integrate the sea ice data into these data sets and serve them for both the North Pole and the South Pole regions. Now, there's also data from the National Snow and Ice Data Center. They focus on data for research, and they don't focus on just sea ice. They also have glaciers, ice sheets, permafrost, soil moisture, snow. So, they have a bigger repertoire, and as I said, they mostly focus on research. And the NSIDC is a tri-agency organization, and so it's basically sponsored by NASA, NOAA, and National Science Foundation. And just as an example of some of the sort of products they have, keeping in mind they focus on research, this is an image that I just took from their website yesterday. So what we see here on the left is sea ice concentration anomalies. Remember if you were at the session last time, we were looking at anomalies, which really help you show how things have changed or how things are changing. And so what you can see here is this is an image for July, so of last month of this year. And these blue regions are the areas where there's negative anomalies for ice. So basically, these are the areas where there's less ice than there usually is, according to a long-term record. And you can see there's actually some areas where ice is actually increased. There's more ice than there usually is, but the decrease of sea ice in the Arctic regions is a big issue, And you can see that graphically. Again, these were images I just picked up straight from the NSIDC website. This is looking at the anomaly of the extent of the sea ice in the Northern Hemisphere. So you can see in this record that goes back to 1980, so we have 40 years of data, there's a steady decline in the extent of sea ice in the Northern Hemisphere. Now, what's interesting is that actually in the Southern Hemisphere, we don't see this. It looks pretty flat. Statistically, there's actually, I guess, a slight increase actually in the Southern Hemisphere. And this is where I have to admit I'm not really a sea ice expert, and I'm not sure exactly why this is, of why we see this really large decrease in the Northern Hemisphere, but not the Southern Hemisphere. We will be exploring more this decrease in the sea ice when we go on to ERDAP, and we'll actually be pulling down some of that data and looking at it ourselves and making graphs similar to this. So the NIC, the U.S. National Ice Data Center, they focus on sea ice data for near real-time uses, for tactical use. So they really focus on looking at ice for navigation purposes. They're also a tri-agency center, and they're operated by the Navy, the NOAA, and the Coast Guard. So really for focusing on ships and transportation that are in these regions and need to know where ice is, where icebergs are, that sort of thing. So they're looking at things on a different time scale in general. This is an animation I got from their website yesterday. And so what this is showing is a 90-day animation of the what they call the MIZ, the marginal ice zone, which is the area in red, which is basically where you have more than 80% of ice coverage. And so you can see how this is changing in the last, in a 30-month period. Basically, as we get into the summer, the sea ice is shrinking. And these plots that they make of the marginal ice zone are actually made, they're not generated by a computer. There's actually analysts who look at a bunch of different data sets. Remember, I said there's a lot of different ways you can look at sea ice. And so they actually look at different data sets and then actually often visually come up with these to determine where the actual outline of the ice zone is. So again, to summarize, there's these different sea ice properties that can be monitored by satellites. We can get sea ice concentration, we can get the thickness, we can get the age, the ice type and the age, and we can get the ice edge, which we were just looking at with the MIZ. And we can get it from different types of sensors. We can get it from visible and infrared, and it's pretty obvious looking at the visible imagery. You can sort of see where the ice is, where it isn't, and infrared. You can also see the imagery of ice. The issues with infrared and visible are that they can't see through clouds. So if there's clouds, you aren't going to get any data. But the microwave data can see through clouds, and so that's really, a lot of the microwave data is really crucial, particularly when you want to get an image every day, and there can be times when it's cloudy for extended periods of time. So SAR is the only data you're getting. So we're going to focus quite a bit on SAR, and actually it's going to be Chris. And so I'm going to turn it over to Chris now. But before we do that, or we will ask you two more Slido questions. And whoops, let me get out of here and go back to Slido. Have you used SAR data before? And I will say yes. Okay. Few people, most of you have not. So those few of you who have, what have you, next question, please, Bill. If you have used it, for what purpose have you used it for? And this is just, type in your answer. Because here, obviously, we're going to be talking about SAR for sea ice, but there actually are a lot of different purposes that you can, or applications that you can use SAR for. And I guess nobody wants to. People are feeling shy. That's okay. Chris, why don't we hand it over to you, and maybe you can just mention some of the other things that SAR is used for, but then you can get into the presentation as well, and just let me know when you want to advance.
Yeah, so I'm Chris Jackson. As Cara mentioned, I'm a consultant scientist at NOAA NESDIS STAR. And NESDIS, as she said, is the environmental data services. They basically operate the satellites and work on getting the satellite data down and into users. And STAR is sort of the research side of the house there. And so my job is twofold. I develop products based on particularly synthetic aperture radar imagery, and then we work to develop that system to get those products out to the customers on any given day. And my particular area of expertise is in microwave, and I've been doing SAR data exploitation here for, I don't know, about the last 25 years or so. And so I'm going to give you a quick overview of the satellites we're using, primarily for this environmental type of work, and then examples of some of the products that have come out and that will eventually find their way onto Polar Watch. And so those of you unfamiliar, so right now we're going to talk about the Sentinel and RadarSat-2 systems, and these are C-band, I call them national SAR systems because they were put up not by private companies but by governments. And so RadarSat-2 is a combination of the Canadian Space Agency and McDonnell Detweiler Corporation in Canada. Sentinel-1 by the Europeans, and the RadarSat Constellation mission is a Canadian Space Agency mission. And as we were just discussing, one of the advantages of the microwave end of the spectrum, and particularly the active microwave end of the spectrum here, is that you can see through clouds, but also more importantly for the North Pole, it's dark for months on end up there as well. And so we need to look in these bands in order to extract the information that we want. And over the last, 40 years since SAR has been developed, these instruments have become very sophisticated in their capabilities, offering a wide variety of collection modes, and I'll talk a little bit more about that on the next slide. And there's a new generation of small sort of X-band SARs that are about to go up, very high resolution systems, not particularly useful for environmental monitoring large areas because their footprints are so small, but very good at getting high resolution imagery that are going to be used to support sort of special operations or disaster response or things going forward. So again, depending on what you're looking for, the SAR can have very high resolution, greater than 3 meters. Typical resolutions are maybe 50 to 100 meters, but we can get them on swaths as wide as 500 kilometers. And for a radar instrument, an active radar instrument, that's a wide swath. As you may have seen with some of the visible imagery that you worked at, it's small compared to maybe the VIIRS or the whole hemisphere of GOES data, but 500 kilometer swath width is considered a wide swath radar. And again, depending on whether you want high resolution or area coverage, there's a trade-off that you're going to make. And just I want to point out here with the table is that these systems, the engineering over the number of years has sort of worked its way, converged. So despite the fact that they were built by different organizations, one's the Canadians, one the Europeans, they actually operate very similarly. They operate at the same frequency, they operate at the same polarizations, they have the same viewing geometry of the Earth. They collect over a wide variety of swath widths, anywhere from 50 to 500 kilometers, as I mentioned. The resolution at wide swath, again, about 50 to 100 meters. And for SAR, it's a coherent signal. So both the amplitude and the phase of the radar pulse are collected, unlike other instruments, which we'll talk about a little bit later, the scatterometer, which is an amplitude-only system. So next slide. So here on the left-hand side is an example of the Sentinel data collection. And so the radar looks off to its right-hand side, and the various yellow boxes are the different collection modes that it can work in. For Sentinel, there's two that we use primarily for the Arctic. It's this interferometric wide mode, which is a 3-beam position mode and allows you to collect a swath width of about 250 kilometers. And then there's an extra wide swath mode, which is a 5-beam position mode, which allows you to collect out to 400 kilometers. And again, as you would expect from an active radar, it transmits a pulse, listens to the reflection, and then, as I mentioned on the previous slide, records both the amplitude and phase. And all of that information is then used to construct the image. And so the time period that a part of a target for, let's say, stays in the beam is going to be the synthetic aperture time, and through the sort of the black magic of Fourier transforms, you can go and you'll get an image like you have here on the lower right-hand side. So that's why it's called synthetic aperture radar as opposed to a real aperture radar, that you're actually literally synthesizing the aperture as the spacecraft moves through space, along its orbit, and you can get these high resolution images, and that synthesizing is what allows the high resolution to be constructed. And so the lower right here is just a picture of a Sentinel-1 image I pulled off the website yesterday. It shows Iceland there in the lower right and the sea ice edge in the upper left. And next slide is just a couple of more examples. And so microwave scattering from the Earth in general is somewhat complicated because of its coherent nature. Sea ice is complicated because of the wide variety of forms it can take over the course of its lifetime. You put the two of them together and it can be a challenge to do SAR image interpretation of sea ice. So the basics, for SAR is that if something is bright, it tends to be rough. If something is dark in the image, it tends to be smooth. And so here are just two examples, again, of some various sea ice manifestations. On the left-hand side, there's a variety of ice types here off northeastern Russia. And so in the lowest left-hand corner of the image is land. Adjacent to the land is what's called Landfast Ice. And so that doesn't move too much, and we see that over the course. Just outside the Landfast Ice, we've got sea ice that's continuing to develop. So the dark ice is sort of grease ice. It's very smooth. It probably has just formed. It's kind of just floating there on top of the ocean. Out beyond that, where the image gets slightly brighter it's a fairly high wind condition. So the sea surface has been roughened and the radar backscatter has been enhanced. And then continuing to the northeast, where it gets even brighter, that's sort of the sea ice that's been established there for some weeks or some months, and you can see that its character has changed. There's some breakage and flows that you can see that make up sort of a speckled pattern up there in the upper right-hand corner. And again, sort of another image just took place just this past December, again, sort of in that eastern part of the Arctic. And you can see again sort of the fractures in the ice along the southern part of that island, and I can never remember the name of that island. It begins with a Z. You can see the open ocean to its north and to the very south, and you can see sort of some of the new ice forming there, which is that dark space in kind of the lower right. But the SAR, again, with its resolution on the order of hundreds of meters or tens of meters, allows you to get this detailed structure of the ice, and you can see the things like the leads that are all broken up here, and we're going to show that more as we move ahead. So I think the next slide. So there's a little bit of a cost for getting the resolution on the order of tens of meters, and for having an active instrument, and that is that the SAR is not on all the time, unlike the VIIRS or the GOES. It has an on-orbit time of about 25 minutes for its 90-minute orbit. And so the system is programmed up, and you get a collection pattern shown in the image here, which is what's sort of typical for Sentinel-1. Here, you get about 600 scenes a day for each of the Sentinel spacecraft, and they've been sort of selected for where they want to be. Now, ESA has an effort to actually collect a lot of data over the Arctic to track these climate changes that have been mentioned earlier. And so we get some really nice coverage. We get about 70% of the day in the Arctic with this. And if you put this over the week, it's kind of amazing that you can get the entire Arctic coverage on a weekly basis at sub-100 meter sample spacing, which if you had gone 20 years ago and told people that was possible, they would have kind of maybe laughed at you. But that's the level of sophistication and coverage that we're now getting with these modern satellites. And we do have to give a lot of credit to the Copernicus Earth Observation Program for putting up a whole series of these satellites. And it has been key to making SAR more accessible to researchers and students since it's gone up in 2014. It's done two things that were really groundbreaking. One is that it put in place a regular collection pattern. So you now know where the SAR data are going to be collected, and you know that the data that's going to be collected today will probably be collected again 12 days from now, which is the repeat pattern of the satellite. And that's been huge these previous systems were more research oriented, and they didn't have these weather these weather meteorological type collection patterns which were taken on a regular basis. And then they turned around and they made the data free and open, and not only free and open, but they committed themselves to near real-time delivery of this data. So if you're looking to monitor on a daily basis, which is what my job is there at NOAA, this has been incredible. So there was a large gap. NBSat was a key satellite for the people at the National Ice Center when it was lost in 2012. There was a struggle to be able to adequately cover the North Pole and derive the products that they needed to do for their customers until the Sentinel systems went up in 2014 and 2016. I think that's it. So again, as we mentioned, there are a lot of applications. We get the ability to look to see where the ice edge is. I'm going to show an example here of ice drift. There was the mention of the MIS. That's actually an active area of research here at STAR that we're on the hook, as it were, to develop an automated MIS detection to facilitate the analysts at National Ice Center. There was a comment earlier on about icebergs. That is actually another significant area of active research inside both our organization and the National Ice Center to automate iceberg detection and knowing where they are. And the synthetic aperture radar is one of the systems that they're relying on because of its resolution and its ability to see both through clouds and in the dark to be able to do iceberg charting and tracking. Next slide. So again, as I mentioned earlier, we have about 70% of the Arctic covered on a daily basis. And one of the things that we do to facilitate the researchers here is we construct these Arctic composites of the normalized radar cross-section, which is the amount of energy that's coming back from the radar signal. And this allows them to take several hundred images and just display it in a convenient manner. We produce this as Cara mentioned, in near real time. We do it every 6 hours, collecting the prior 24 hours of data, and we produce it in a polar stereographic projection with about a 250-meter sample spacing and provide it to National Ice Center for use by their analysts. So this is one of the products that's in development for Polar Watch. We've got the history going back to 2016 with the Sentinel spacecraft, and we're looking at packaging this up correctly and getting it put into Polar Watch, hopefully here over the next, I'm hoping 12 months. We're working so we think this is going to be something that users are interested in for their analyses. So I think next slide.
And now we're going to.
Yeah, we're going to show an animation. So again, one of the nice things about getting this data on a daily basis is now you can track changes from day to day. And this is I think it's a 10-day image that I constructed from data back in 2016, and there's a whole series of features if you can sort of look past the flickering effect due to the moving swaths. So in the lower corner is the top northeast corner of Greenland, and you can see if you look closely, you can watch the sea ice moving sort of southeast around the corner of the island down into the Fram Strait. And again, this is only about 10 days of data, so each flash here is just 1 day, and it's amazing how fast the sea ice here can move. It can move up to 20 or 30 kilometers a day. You can see as you kind of move north into the eastern Arctic, the ice goes in a completely different direction. It's sort of beginning to move to the north, I guess to the east there, sort of to the top left-hand picture of the image, and you get to watch these ice features along the ice edge as they migrate. And if you look really closely, you can begin to see some of the things that I showed in one of those previous images, that new ice is being formed. This is so this is right after sea ice minimum, and the sea ice is just beginning to grow at this point at the end of September, and so we're beginning to see new ice along the ice edge. Yeah, I don't have any other comments on the.
Go back to the point.
Yeah. So while the eye can pick that up and it's fascinating to watch the ice move, we'd like to turn that into a useful product for, again, sort of our customers. And one of the things we've been working on and that has been worked on for a number of years using other microwave techniques, has been this sea ice drift vectors. And so we take the imagery from day to day, and we have a correlation technique that actually will identify particular features and relate them from imagery from one day to the next day. So we do this on a 1-day interval. There are different ways to do it. There's an OCSAP product that actually does a sort of a 2-day interval, and you can produce these ice drift vectors. And so what you see here is each yellow line here is one vector that has been derived from data that have been taken place on 2 sequential days at that location. And then just sort of in the lower left-hand corner, just for information purposes, we put sort of a histogram of the sea ice speed or the drift speed that was calculated there. And so you can see there's a peak there a little after 10 kilometers per day. And there's a larger peak sort of in about the 1.5 to 2 kilometer per day. And so there's a lot of ice that's not moving, but there's a small section of ice then that is moving relatively rapidly, with even a few areas of the Arctic out at 25 or 30 kilometers a day. It's kind of amazing to watch this stuff move as quickly as it can. I don't think people really think of it in those terms a lot of times. And so again, this is something we're producing for National Ice Center. It's continuing to be evaluated and refined, and we produce a shapefile with it that is what you see here in the yellow. And if we zoom in, which is the next slide, and this is an image from the Beaufort Sea back again in January of 2020, and so it's an image pair. And Cara, if you toggle sort of the arrows, it should toggle the there you go. Oh, yeah, just back and forth with the two keys, right? And so again, this is, you can see this is what's called sort of a lollipop plot, and so the circle is where it starts, and the line or the stick of the lollipop is the direction that the ice is traveling. And you can see here, just over the course of a little less than 24 hours, these large leads that are opening up in the Beaufort Sea north along the Canadian archipelago as the ice moves sort of to the northwest there. All right. So again, we mentioned, and part of the purpose of this meeting is to make you aware of where these data sets are resident. And so, as Cara mentioned, we're working to get a lot of them into Polar Watch, so the data are available there. The SAR data for the U.S. coastal waters and parts of the Arctic are available through the Coast Watch webpage. You can search for the Level 2 SAR data. The full Copernicus archive is available through the Europeans through their Scientific Data Hub, and again, that's free and open. They're going to require you to register, but once you've done that, you can download the full resolution imagery from ESA. The actual Copernicus archive goes back a few years, and then some of the older data are actually being, there's a parallel archive at the Alaska Satellite Facility, again, where the data are free and open. And the Alaska Satellites Facility online archive goes back a little bit farther than the Copernicus. You can get anything out of Copernicus beyond about a year or so. You'll have to just wait for it to be delivered to you within about a day instead of it being readily available for downloads. And again, another example here of an image from the southern hemisphere, a Sentinel-1 SAR image of the iceberg A68, which calved off the Larsen ice shelf back there in October 2017. So next slide. So we mentioned SAR and its abilities here and its features of having its high resolution. But as I mentioned, the Sentinel spacecraft have only been on orbit since 2014 and 2016. And while there is a record of the C-band SARs going back to 1991 with ERS-1, but Arctic coverage is not as maybe complete as you want. And one of the systems that has been used to do sea ice work over the last 35 or so years has been scatterometry. And so the scatterometers are put in orbit, to observe ocean wind speed and direction. And so it transmits a pulse, looks at a particular spot on the ocean at several different geometries, and then can back out based on the normalized radar cross-section, what the ocean wind speed and direction are. And so ASCAT is one of those instruments. that is currently up and doing that job. And it has the advantage, from my perspective, from a research perspective, that it operates very, very similarly to the synthetic aperture radars that are up. It's a C-band system, almost at the exact same frequency. It looks sideways the same way that the SARs do, in almost the same incidence angles. It has very similar swath widths, and so these data can be sort of used together when you're doing some of your research. The downside is that it is an amplitude-only signal and doesn't have the phase information, and so its resolution, because it's a real aperture radar that you're actually only seeing what the actual aperture, the beam width of the radar encompasses, is on the order of kilometers and not meters. And so it's nominally 25 kilometers, but there's a special processing that allows you to get it down to 12.5 kilometers. And just there in the lower left-hand side is an example of some scatterometer output, and those are wind barbs indicating the wind speed and direction of the ocean surface winds that were acquired at that time. But next slide. But so with all this data, there are some smart researchers out there, and one of these people is David Long out at Brigham Young University, and he has found a way that allows you to give up a little bit of temporal resolution and to increase your spatial resolution. And so he developed processing that he does at BYU and is also instituted at NOAA that produces a 4.5 kilometer NRCS sort of image from the scatterometer data, and you can kind of see that as the inset in the upper right-hand corner. The advantage of the scatterometer is that it covers the entire Arctic every day, and in fact, because there are so many of them up there, it actually covers it several times a day, so we get almost the same map from each of the MEDOP ASCAT scatterometers. And that can be used for sea ice classification and sea ice study. And the scatterometer has the advantage that it does go back in time of a record of almost 30 years. So if you're interested in climate type timescales, before ASCAT, there was sea winds and there was adios. And so all of those data are available for use. We take the data here from ASCAT at NOAA again and turn them into a sea ice classification product, for which there are 3 classes. We have a seasonal ice, which is ice that will disappear every year. There's the perennial ice, which is ice that will survive a melt season. And so that's the longer term ice that's there, and that's white in that picture. And then sort of the mixed ice, because it doesn't transition from perennial to seasonal, sort of cleanly over a 4.5 kilometer swath. Sometimes the pixel can have information from both of them. But this is another product that we produce internally at NOAA that's used by the researchers to guide, and we help them, and we deliver it to National Ice Center to help their ice analysts. Again, the only other point, the advantage of the active microwave instrument sort of is resolution. We're not going to discuss it, but there is passive microwave, and those data typically are collected on the order of 25 or 30 kilometer resolutions. And so it's very useful to have the active instruments again, because we can get 4.5 kilometers with the scatterometers and tens of meters with the SAR. And I think that's the last. Is that the last slide, Cara?
Yes, it is.
Yeah.
Why don't we? Can weird echo. Why don't we go to Slido and see if there's any questions that anybody had on any of that? I thought that was an awesome presentation. Thank you, Chris. Yes, we do have some questions. Is the coast watch for when sea ice melts and causes the seawater to rise?
The Coast Watch program in general at NOAA is to allow a single portal for users to access a variety of the satellite data to look for things like the effects of what happens with sea level rise. I think that's the whole point of the question.
Yeah, I mean, Coast Watch it was started back in the 90s, and as the name implies, it was literally to look at coastal waters in near real time. Actually, how it was started was there was a harmful algal bloom going on off the east coast of the United States, and there was dolphin kills and some other things going on. And at that point, there was not ocean color data. There was only sea surface temperature data. And it wasn't, in those days, it wasn't processed quickly enough that that scientists could look at yesterday's, sea surface temperature data like we can now. So, but they wanted to look at it to see if there was anything odd going on in the water that was making these harmful algal blooms. So the processing was put in place to make it so that you could get a quick image of yesterday's data. So that's how the name implies. But it's really, traditionally, Coast Watch has not really had ice products in it so much because it's primarily been the coastal areas of the United States. Although the Great Lakes node does have sea ice products in the Great Lakes. So there was another question, what type of users make use of SAR data? So we did mention there was that question of other applications. Do you want to briefly mention the other things that one can do with SAR data, Chris?
Yeah, so there's a wide variety. We can give a whole presentation on that at some point, in the future. So my particular area before sea ice was doing ocean surface winds, and similar to what the scatterometer does, the SAR does the same thing, but at higher resolution. And we've been working with people in the National Weather Service that are interested in getting that. We have a tropical cyclone product to get hurricane winds out of that and deliver to places like the Joint Typhoon Warning Center and the National Hurricane Center. There's a wide variety of land use. In fact, both the Sentinel mission and the upcoming NISAR mission are what are primarily referred to as, quote, solid Earth missions. And so they're looking at the crustal dynamics. And there's a mode that they operate in, this interferometric mode, where you can track the motion of the Earth's surface down to the centimeter type level. So that's another application. It's used for vegetation classification. We've been using it to look at fires. You can see burn scars from fires in the synthetic aperture radar. Again, with high enough resolution, you can do things like coastal flooding. We have a coastal flooding application, and so it has a wide variety of uses that we could talk about for a long time.
You could also, isn't another use of tracking oil spills in the ocean? Yeah,
so that's right. So we're sensitive to the ocean roughness, and oil damps the roughness of the ocean surface, and you can determine if there's a surfactant. And so we see both natural surfactants from things like fish oils and other biological sources. We can see natural seeps from places like the Gulf of Mexico. And we can also see pollution events from spills from oil platforms or from ships, because they show up as dark features on the SAR image.
So let's take this fourth question. This is still about SAR. Is the biggest benefit of combining SAR and scatterometer data to improve coverage in areas where SAR is not available? Are there other benefits?
So fortunately for ASCAT and Sentinel, they operated very similar frequencies, and so we can use sort of one to fill in for the other. But in general, they were designed for two separate purposes, even though they operate very similarly and there's some overlap. So the scatterometer was designed to do ocean surface winds on a global basis daily, and the synthetic aperture radar was designed to do, again, things that require higher resolution, look at more detailed features on the ocean surface. We can even resolve another application. You can resolve the swell wave field typically. So they're complementary, and so there is some benefit to combining them, again, to as you mentioned, to improve the coverage, because the SAR is limited in its duration. And then there's the other question there: is there enough sea ice to track year-round? And the answer is currently yes. So the Arctic does not become ice-free in the summer. There is sea ice there all year round. That's that perennial ice that I mentioned. The signal becomes a little bit more complicated in the summer because the surface melts a little bit. You get some melt ponds and you get some other effects that interfere, that you get some other phenomena that result in a unique signal in the summertime that makes maybe doing the ice classification a challenge versus in the time between sea ice minimum in September and when it finally starts to melt in early June.
Great. Well, let's move on then. And we're actually, in the next part, we're actually going to be looking at some data on polar watch, and we can actually look at the distribution in the Arctic. So let me go back to the PowerPoint for now. I did just had a quick video here. Again, this is a little animation I got from NASA's Scientific Visualization Studio. Just a segue, we're going to go into now looking at these longer time periods and looking at the long-term trends. And so what the animation is showing here in the back is it's showing you every year the sea ice minimum. And so this started in 1978, and you can see every year how it's basically decreasing. You know, there are some years when it goes up again, but generally overall it is decreasing the amount of sea ice minimum. And Chris just alluded to that. Obviously there's seasonal changes. The time of year when there's the minimum amount of sea ice is September. And so basically these animations are taking September of every year, or the month when there's the minimum, because that's just the sort of easiest way to look at that. So we're going to delve into this a little bit more in this next section. This is just bringing this point again of, this is an image I got from the NSIDC website. And what this is showing you is the seasonality of the Arctic sea ice extent. So you can see that it's basically, there's a maximum that occurs in March, and then the minimum occurs basically in September. So you can see that this basically happens every year. What they have color coded here is the years of this. So the lighter colors are basically the decade from 1979 to 89 up here, and then the darker years, 2020 is this the sort of really dark pink line here. So you can see over the 30-40 year record we have is that there is this decrease in the extent. There's a decrease in the wintertime when there's that maximum extent, and there's also a decrease in the when we have the minimal extent. But generally, to track it, generally one looks at the minimal extent of the sea ice, and we're going to do that next. We're going to generate some sea ice concentrations using the data that we're going to get from Polar Watch. So to do that, I am going to actually jump out of here, and I'm going to do the live demo part. I'm going to go to my browser, and I'm just going to go to Google, and I'm just going to Google Polar Watch and NOAA. And this brings up the main Polar Watch page, and I'm just going to go to the catalog. And as I said, we have Polar Watch has more than just ice products. We have other satellite data, but we're just going to focus on ice for the moment. So this gives us a listing of all of the ice products we have. What I want to look at is we have near real-time data. We have climate data records, which are data that go back the longest. And that's what we want to look at. We're going to want to look at sea ice concentration from NSIDC. We want the climate data record, but we want it not from Antarctica. We want it for the Arctic. And so that is down here. And so I'm going to go to the portal. We have this in a daily or a monthly file, so we want to look at the monthly file because we're going to be looking at a lot of data. So this automatically comes up and it brings us the most recent image. So this is thinking, and it's going to come up with the sea ice concentration for December of 2019. This is the climate data record, so it doesn't have the most recent data. If we wanted to look at the most recent one, we could look at the near real time. But this is showing us December of 2019. So let's look at the differences in the minimum extent. So as we were just talking about, that happens in September. So let's change this to, rather than December, let's look at September of this year. And so this is the minimum extent. So this answers that question somebody has, is there enough ice year-round in the Arctic to track. And yes, because this is the minimum extent, and so you can see there still is ice here in September, but this is the generally the time of year when there's the least ice. So let's go and see how this compares to data from, you know, several years ago. Let's go back and look at 1989, so 30 years before. And so you can see here, so this is the same month from 30 years ago, and there is definitely more ice here than we're seeing now. Now I know it's kind of hard to compare that. Let's go and look. I actually saved it as a screenshot. Whoops. There we go. So we can look at them side by side. So this is September of 2019. This is September of 1989, 30 years earlier. So you can see there's quite a big difference, particularly in this area over here, but also in basically the ice edge above the Bering Strait. So there are, you know, these are significant changes we're seeing. But, you know, maybe we want to look at this sort of like in a time series. How would we do that? Well, to do that, it's a little bit easier to do that on ERDAP. So we're going to go down to data access down here, which shows you how the links to ERDAP. So we're going to click on the monthly data, and this will bring us to the ERDAP page. This actually brings us to the metadata page. So this gives you all the information about this data set product. If we want to graph it, we just go to the Make a Graph page. Now, this is a projected data set. So when we were looking at it in the Polar Watch portal, the first time we looked at it, when we were just looking at it, it had that nice, you know, round projected image with latitudes and longitudes. But the data is actually on this grid. So here we're seeing it in the on the grid projection. So rather than latitude and longitudes, we're actually seeing meters from the North Pole. So it's a little bit more cumbersome, and it's kind of a little harder to kind of wrap your head around. But this is how the data comes if it's in a polar projection. So we can see this is basically this. This is that same image we were looking at, only with this slightly different projection. So this is December of 2019. And so what we want to do here is let's look at a time series. Let's pick one point. Now remember, it was this area here where there was kind of like the most changes. Like here, there's ice in, well, let's go back to September for consistency. So this is September. It's going to show us September of 2019, and see how there's no ice in this area here in the I believe this is the Cara Sea. Now if we go and look at 1989 in the same area, you see that there is ice here. So this is an area where there's quite a bit of change. So let's make a time series in this area. This is also a nice area because on these projected coordinates, it's a sort of nice, easy number. They're both about, the X and Y grids are about 1 million meters from on both the X and the Y. So we're going to change our graph type to lines and markers. And we're going to make, we're just going to specify one value. So this is basically just one pixel that we're looking at in that area. And let's have a nice time series here of the entire data set. And then we're going to redraw the graph. So here's the time series. So it looks a little messy at first, but we have to keep in mind that, you know, this is showing, you know, seasonal data. It's showing the data throughout the year. And so we know there's a big difference between the minimum and the maximum. And what we're really seeing, we can see these changes here. It does look that over time, there's getting less ice in this area. But there's also times when there's a lot of ice there. And that's because of the seasonality that we're looking at. So we can do a little cheat in ERDAP. It's not really a cheat, it's a trick. If we just want to look at, say, 1 month of the year, we can do that. If we go to the data access form, when we go to the data access form, there's this stride that's available. And so this is a data set that's monthly. So if we set this stride to 12, then we're going to basically get every always get the same month. So we're going to look at September from 1989 to September of 2019. So this is just going to give us data from September, which is the minimum, the time period when there's the minimum ice. So now if we select our file type to be a large PNG and hit submit, so now you can see that you can see this a little bit easier. We have there are times when we have basically the beginning of the record, there was almost always ice in this area, but now there's quite a lot, a lot of times there's not ice in this area. So you can see that these changes in the sea ice extent. Okay, so this is just data at 1 pixel. And obviously, if we really want to do more robust analyses, we want to get a bunch of data and probably average it, or maybe look at one area and see how things are increasing there. So to do that, let's go quickly to R. And so I'm going to go to R. And I know many of you don't use R. R is a programming language. You can make figures, you can do analyses. I put together a notebook, and again, the file is on the course website where you found your homework and all that other stuff. And what this notebook does is it lets you puts in the code, and then it displays the results all in the same place. So what this is going to do, this code is, it's going to go in, it's going to get that data we were looking at an RDAP, and it's going to select just one area. It's going to select the data from the around north of 75 degrees north, and map up and average the sea ice extent in that area over this time period, so we can see how ice is changing in that one area. So basically what this code is going to do is, in R, there's always all these packages. If there's anything you want to do in R, chances are somebody has written a package that makes it easier to do. So what we're looking at here, just to sort of give you a little layout of how R works. This is Rstudio, which is a really nice way of working in R. It gives you, in this window up here, the code, the script that I'm working on, that I'm saving. Down here is the console, where it's going to basically run those commands. Up here, it shows you the global environment. So it tells you what variables you have. It tells you what they're called, what they do. And then down here, it has a list of packages, available packages, and it tells you if they've been installed or not. So the first thing I'm going to do is in this script, there's 2 packages that I actually use. It's the NetCDF4 package, which helps you open NetCDF files, and then this OpenAir package, which actually helps you average data annually, which we use later on. So what this section of code is doing is it's saying which packages I want to use. It's checking to see if they're installed already, and if they're not, it's going to install them for me. So in a notebook like this, if I hit this little green arrow here, it's going to run this current chunk of code. So this code is just going to basically install some packages if they're not installed. So I'm going to hit that, and then it comes down here, and basically it doesn't really show anything because it installed those packages for me. So the data that we're going to get is projected. So remember when I showed it in the first time I showed it, it was on that nice circular map that showed latitude and longitude. And then when I showed it in RDAP, it was on this grid that was, values of 4 million, because they were meters from the center. So when we're working with projected data, if we want to think about it in latitude and longitude, we have to get this grid to do that translation for us. So what this code is going to do first is it's going to download the latitude longitude grid associated with that data set. So that will allow us to map our latitude and longitude constraints to the grid constraints. So this first thing we're going to do is download the grid. So that's what this next thing does. And the other thing that this is doing here, and this is very useful, somebody said that what they wanted to get out of this was understanding how to work with R and RDAP, is this is showing you how to put together an URDAP call to bring data into R. So if you remember when I was talking about URDAP in the last session, or if you reviewed the URDAP tutorial, all of the URDAP requests are RESTful, which means it's entirely constrained by the URL. So what we're doing here is we're putting together a URL that will get this data. So the first thing we define is the URL. So that's the URL, the base URL of PolarWatch. So that's polarwatch.noaa.gov URDAP/griddap. If you wanted to get data from a different URDAP, like for example, the West Coast node that we talked about last month, you would change this base URL here. The grid ID is saying which data set you want. And so in this case, it's the NSIDC CDR Ice for the Northern Hemisphere. And in this case, we're getting the grid. This is not getting the data, this is getting the grid. And then this is just pasting all that information together. These are the ranges of the X and Y constraints. So it's saying, get me the entire grid. It's going to then download that file and then read this. This is just basically reading the netCDF file that it's going to download. So I'm going to hit this arrow and it's going to do that. Down here in my console, it tells me it's trying this URL. It did, it downloaded 2.1 megabytes, and it basically read that file. So then the next thing we want to do is we want to just look at a subset of this data. So for this exercise, I decided to look at sea ice concentrations in the area north of 75 degree north. So what we need to do is we need to figure out what the latitudes north of 75, what that relates to in the index range. So that's what I'm doing in this next part, is I'm saying, get me the indices where the latitude is greater than 75%. And then I'm figuring out what those are in the grid. So I will run this here. And now that I have those indices in index space, I'm going to go and get that data. So this next call here is note how the data ID has changed, because it's not the grid now. Now we're actually going to get the data. And in this data set, there's actually multiple variables. And so I'm going to get the sea ice concentration, monthly CDR was the name of that, the data that we were looking at previously. I'm going to get all of the data. The data goes back to 1979. And then here I'm pasting in the indices that correspond to data above 75 degrees north. So I'm going to run this. Now this is getting, that just actually pieces together the call. Now I'm actually going to download it. This is going to download about 32 megabytes of data, so it might take a few more seconds than getting the grid data. But it's telling me in the console what it's doing. It's trying this URL that we've pasted together, which is going to get this chunk of data for us. And of course, it always takes longer to do these things when people are watching you. Okay, but it's done now. So what that did is that downloaded a netCDF file, and now we're just going to read it. So that's what this next code is doing. It's just reading that netCDF file. And now we are going to, so now we have this data. This data is roughly on a 25 by 25 kilometer grid. It's not exactly, but for this purposes, which are sort of quick and dirty, we're just going to assume that everything, every grid is the same size, so that if we just multiply this by the size of that area, we will get the sea ice extent. So we're going to use a threshold of 15%. So we're going to basically count out how many grids have more than 15% of data. So that's what this next piece of code is doing. And then we make a quick plot, and this is what we get. Now this looks kind of ugly when you first look at it, and part of that is we can see that there's actually, even though the data went back to 1979, in this TDR there's some missing data in the first part of the extent. So we will actually, the next part we'll omit this data from the analysis, so it will be a little bit easier to look at the results. And then again, there's this seasonal signal, right? So a lot of the time in the winter time, there's ice extent is over the whole area, but then in the minimum is really what we're seeing the changes in. So what we're going to do is we're going to calculate the annual minimum ice coverage. And for this, I'm using this package that actually looks at over a year, and you can get the minimum or the maximum. We're subsetting the data first to just get data after 1989, and then we're just going to average it and get the minimum and the maximum for each year. So that's what I've done now. And then next, we'll just plot the annual minimum. And so that's what we see here. And so you can see this significant decrease in the minimum sea ice extent that we get every year. And again, this is this area just north of 75 degrees north. I realize that was really quick, and particularly if you don't know R, but I just kind of wanted to show an example of a way to do, how you can get data from ERDAP and bring it into a plotting package and do stuff, because one of the nice things about ERDAP is, yes, you can make quick and easy, quick and dirty plots. You can make those time series, but a time series at one pixel location is really not the most robust way to do analyses. I mean, really, honestly, what you want to do when you're getting with data is to bring it into some sort of package and do your own analyses. And so this is just showing you an example of doing that. So that is all I had to share. I'm happy to take any questions. Maybe we can go back to Slido for that. So let me do that. Okay, why is there always a circle blank in the center of the polar region in the sea ice image? That's just a question of the gridding. When you're actually at the North Pole, at 90 degrees, it's just a question of the projection, that's all. I don't think I'm explaining that very well. Does that make sense? Chris, do you want to help me out here? Is Chris gone?
Say that again. My dog was negative me.
Oh, sorry. I was not doing a very good job of explaining why there's always that blank circle in the center of the polar region.
Yeah. So that's a data collection limitation, actually. So these satellites are in polar orbit, typically a 92 to 94 inclination orbit, and the sensors just don't see to the North Pole.
Okay.
And so that's why there's that little gap there. You can see the older data had a larger gap because the scatterometer instruments at the time didn't go quite to the pole. The more recent images get closer to the pole, but that's where that gap is. There's it's just a sensor limitation that we don't see the North Pole.
Any other questions? No other questions? All right, well, okay, no, thank you for a thorough explanation of R code, great. And if you are interested in, for those of you who are interested in R, learning R and ERDAP, we have a whole tutorial. And so, I mean, that was a really kind of, what I showed was quick and dirty. But if you have, well, actually, you should have the link, because as the homework, I asked you to look through that one chapter. And I had you look at that chapter because it was the one talking about the projections. But we have a whole bunch there that show you how to do stuff, that do various different stuff of getting blocks of satellite data and making time series or making average graphs. So I really highly suggest, if you're interested in that, and I can show you the that link for that. It's coastwatch.pfeg.noaa.gov/project/ERDAP. That's our tutorial about ERDAP, and that I went over a lot of the stuff in here last month. But if you just replace ERDAP with R, you have all the R exercises. So we have, we show you how to extract data within a boundary. So like maybe if you have a marine protected area or some area that's not just a box, we show you how you can do that. And so that does things like, quickly scroll through there. So what we're doing here in this example is just getting this chlorophyll data, satellite chlorophyll data within the boundaries of the Monterey Bay National Marine Sanctuary. You can also do, a lot of our users are in fisheries who have tagged animals, and they want to match up satellite data to the animal track or maybe to a ship track. And so we have a package and a code that makes it a lot easier to do that. So just to go through the example, this is showing a tagged marlin that was tagged in Hawaii and then swam over to the coast here. And the dots here are the locations where the marlin was tracked. And then this is the dots correspond to the value of the chlorophyll data that was most synoptic with that value. And so this is, just plotted up with a few lines of code. And then matchup of satellite and buoy data. And then the one I actually asked you to do was projected data sets. And so that did a lot of what I was just doing, of basically getting that grid, doing that calculation between the grid and the latitude and the longitude. Okay. Now then where, I lost my Slido. Where did Slido go? SatMOC. Got this wrong. Oops. What happened? There we go. Okay. Since this is the last part of the SatMOC training session, I was wondering if there were more of these kind of training sessions planned for the future. That is an excellent question to answer. To end with. Gary, do you want to actually talk about that?
Yes, Cara. Of course, we have an organizing committee here that prepares these training sessions. And after this session here, we're going to think of maybe concentrating on the future training. And our initial thoughts right now is our next training session will be held in probably the first half of January during the winter break. And we're still deciding what topic we would like to discuss. So if you have any suggestions, please let us know. As soon as this training session is over with, I'll be sending out a survey, which will give you an opportunity to put that information give information to us. That's all I was going to say.
Yeah, and so just to reiterate that, you've been getting those surveys after each session, and we really appreciate those. And it's really helpful for us to get that feedback, particularly too about don't be shy about saying if there were things you didn't like, because if there were things that we can't improve if we don't get constructive criticism. So we have been reading the evaluations we've been getting, and so don't be shy about giving us your feedback. And particularly, we would like to know about things if what you'd like to see more of in the future, what you thought was helpful, what wasn't helpful, and what you'd like to see more of. Any other last questions or comments? We never did have a break, so we can end a little early if there's no more questions. Or
John, did you want to make any closing comments?
You might remind people that this has been recorded. They can go back and review it or send it to people or whatever.
Yes, and we'll have the recording up here probably by tomorrow.
Okay.
Okay.
Well, thank you everyone for coming.
Yeah, thank you.
All right. Bye.
Bye, Cara.
Bye.
OK， 行，那就先这样啊。我把你完了你自己斟酌了啊。当然你就说我 improve 你不 invite 早就不 invite 在这个 and we have been continuing work with him and 对吧？你就说这个就行了，完了，好，你不用害怕，你这个本来就是这样啊，好，先这样啊，好，谢谢你，OK，拜拜。